Okay. Hi guys. Good morning. Hope you're able to hear me. Yes.
Yes, sir.
Okay. Cool. So I'll just go share my screen. Start right away. Okay. So hope you're able to see my screen. Okay. One second. Okay. So people, hope you remember we have been doing thermochemistry, right? So we'll quickly do some couple of problems and then we'll go for the third part of the chapter, right? Okay. So this is what is given to you people. So they have given first reaction N2 plus 3H2 gives 2NH3 and the delta H for this reaction is minus 91.8 kilojoules, right? Second reaction 4NH3 plus 5O2 gives 4NO plus 6H2O and delta H for this is minus 906.2 kilojoules. And third reaction, you have 2H2 plus O2 gives 2H2O and delta H for this reaction is minus 483.6 kilojoules. Now what they're asking is for this reaction, right? What is my delta H, right? So this is the question, people. They have given you three reactions, 1, 2, 3. This is 91.8. Okay, if I can rewrite again. Okay, so they have given you 1, 2, 3 reactions, and they're asking you what is the enthalpy for this reaction. Okay, so we have already done this kind of problem. If you can remember, we did like a couple of problems based on this. So now you are going to do it. I'm going to give you 2 minutes time, right? Or even if you don't give me the value, so if I call it delta H1, delta H2, and delta H3, right? Now tell me the answer in terms of delta H1, delta H2, and delta H3. Even though if you don't, obviously, like all you have to add or subtract, right? So I told you what you have to do in this kind of questions, right? So look at the required equation and look at what is there in the reactants and products. Say N2 and O2 are in the reactant side, NO is in the product side, right? So just see where is N2, where is O2, where is NO in the given equations, right? And obviously you have to look for the number of the molecules. Also say here it is 2, so make sure that you have only 2, right? So go for it. I'll give you 2 minutes time. Okay, actually, hope everyone is there. Hope everybody is doing it. Please do not sit idle. Hope you know that I can myself unmute yourself. I mean, unmute you, or I can even ask you to open up your cameras. So don't do the problem because of that. Still, right? I still have those options. Yes. Any answers?
1 minute, sir, doing.
Yeah. will be something in the chat also. Check that. Nothing. Yes, anything? I'll give you last minute and then I'll start doing it. Okay. I think any answers, people?
So I got stuck, sir.
You got stuck. Okay. That
Yes, sir.
happens. That happens in this kind of problems. Let me help you. Okay. So anyways, it's good that you tried. No issues at all if you don't get the answer. Okay, fine. So let me go for it. So I have N2 in the reactant side. So in the first reaction, I have N2. No issues, right? Now, if you look at O2, O2 is there in two of the reactions and it is there in the product reactant side. So we'll just keep it as such. Okay, we'll see what we can do about it, right? Now, next thing what I can go is for NO, right? Now, NO is in the product side. Yes, in the given reactions also, it is in the product side, right? But what I see is that I require two NOs, but there are four NOs in the given reaction, right? So what will I do is I'll multiply this reaction
1/2.
by 1/2. Okay, I'll multiply this reaction by 1/2. Okay, I'll keep it, right? Now, fine, let me write the reaction. The second reaction alone I'll write again, that is multiplied by 1/2. So I will have basically 2 NH3. What happened? Okay, so 2NH2 plus 2.5 O2 gives 2NO plus 3H2. Yes, okay, right. So this is what is the equation, and obviously this would have become delta H2 divided by 2. This is what would have happened to the second equation. No issues. Okay, now I have 2NO in the product side and N2 is sorted. O2 alone we have to see, right? Okay, so for O2, I require one O2. Yes, right? Okay, now I have to see what I can do. Oh my god, this is having bad below. Okay, I will manage. Cool. So what I was telling, so O2 alone has to be taken care, right? Okay. Now what I can do is now if you look at this people, right? See, okay. Now if you just add equation 1 and equation 2, obviously multiplied by half, if you add them, what now you'll get extra? We'll check, right? What will you get extra? I mean, this is the required equation. I just want N2, O2, and NO. Other than that, if I add these two, that is 1 and 2, if I add, I will be getting ammonia extra, right? I'll be getting H2O extra, which I don't want in the equation, isn't it? So what I have to do, I have to
Sir,
make sure. So
sir.
yeah, tell me, Kannan.
Sir, how will ammonia be excess, sir? Will it get cancelled no, in 1 and 2? Since
Yes,
ammonia
sir.
is in reactant.
Okay, fine. In this case, ammonia gets cancelled. Yes, 2 here gets cancelled. Okay, correct. The H2O is still a problem, isn't it?
Yes.
Right. So for H2O to get cancelled, now I have 3 H2O. So I should have 3 H2O in the reactant side. If I have this H2O here, right, then it makes sense. I'll be able to do something to cancel it out, right? So anyways, I need to have 3 H2O, but here I have only 2 H2O, isn't it? Right. So what I'll do is I will reverse this reaction. Okay, this reaction has to be reversed, right? And if you reverse it, you'll get 2 H2O in the reactant side, right? But what I want is 3 H2O. So you are not only going to reverse this reaction, you are also going to multiply by this by 3 by 2. Yes, makes sense.
Yes, sir. Understood,
Right.
sir.
Right. So again, I repeat. So if I add 1 and 2, yes, my N2 is sorted, O2 is sorted, NO is sorted because we have multiplied this second reaction. What I get extra is this NH3, sorry, H2O, right? So, and if I have multiplied it by 1 by 2, I get 3 H2O, right? And if you look at the third reaction, H2O is there in the reactant, product side, which I don't want because I want to cancel it. So first thing you will do is you will reverse the reaction. And also you need 3 H2O. So you'll multiply the third equation after reversing by 3 by 2. That's it. Now, if you're going to add all these three, that is 1 and 2 multiplied by 1 by 2 and 3 reversed and multiplied by 3 by 2, you are going to get this equation. You can just blindly trust it. Right? So how will I write this delta H? The required delta H will be delta H1 as such. Right? Now I have multiplied the second equation by 1 by 2. So it will become delta H2 divided by 2. Right? And third equation, what I did? Third equation I have reversed. So it become delta H3. And it's not only that, I have also multiplied the reaction by 3 by 2. So it will be 3 delta H3 divided by 2. This would have been the answer. Okay, right? So hope everybody got it, what we did here. Yes or no?
Yes, got it, sir.
Okay, pretty simple. Like maybe you would have gotten struck only with this H2O, what you have to do with H2O,
Yes.
right? So other than that, everything is pretty simple here. Right. So I want everybody to give me a yes, at least in chat, or you unmute yourself and tell me whether you understood or not.
Understood.
Okay, 2 are over. I still have almost 6 people.
Yes, sir.
Yes, sir.
3, 4. Okay, then
Yes, sir.
5, 6. Rahul told me. Okay, I think, yeah, that's it. Right. So 6 plus 1. One more. One more. Okay, fine. I'll assume that that person is busy. Anyways, so this is the problem. Okay, do one more.
So what's the final enthalpy answer, sir?
Oh, you want the answer? You have to calculate.
We got minus 41.3, sir.
Minus 41.3. Oh, ouch. Minus 41.3. No, I think I have. I think is there something doubling you have to do because the answer is, I think.
I made a calculation mistake.
Okay, no issues. If you just get this delta H1 plus delta H2 divided by 2 and 3 delta H3 divided by 2, yes, if you just do the calculation properly, you should be, I think, getting minus 90.25, I guess. Right? Anyways, you can just do the calculations later, no issues at all. Okay, fine. Now we go to the next problem. Guys, give me a moment. This earphones of mine is having less charge. Let me change the earphones. Just give me a moment. Guys, you're able to hear me?
Yes, sir.
I guess no. Okay, guys, are you able to hear?
Yes, sir.
Guys, are you able to hear?
Yes, sir.
Shruti is speaking, but I'm not able to hear. Why is it like this? Once again, okay, guys, speak something.
Sir, can you hear him?
Okay, fine. So I'm not able to hear you properly, but anyways, we'll manage with this. I'll just, no problem. Okay, so next problem. Okay, so they have given delta HF of SF6. This is called sulfur hexafluoride is minus 1100, and that of S, that is sulfur atom gas, is plus 275 kilojoules, and that of F gas is plus 80 kilojoules per mole. They're asking what is the bond dissociation energy. Oh God. Bear with the background noise, it will be over in some time, right? So what is the BDE of SF bond in SF6, right? So this is what they're asking. Okay, now this kind of problems also we did, if you can remember. So try to write the reaction for bond, and even though they're asking bond dissociation energy, but you write the reaction for bond enthalpy, SF6 converting into whatever it is, right? So that is my overall bond enthalpy, right? And you know, I think how to connect your bond enthalpy with the bond dissociation enthalpy, right? So again, that will be equal, that or that overall enthalpy of the reaction will be, I can write it in terms of enthalpies of formation, right? So that's how you're going to get the answer. So all these are delta HF values for SF6, for sulfur atom, for fluorine atom. Okay. Now I'm gonna ask someone. Whomever is doing the problems, continue doing the problems. But I'm
Sir,
gonna
I have a
ask.
doubt.
Yeah, Kanna, tell me.
Sir, first we have to find bond enthalpy and then do, sir, or
Yes, that's how you have to do it. Basically, they have given you bond dissociation enthalpies, but doesn't matter. You know how to write the bond enthalpy for SF6. You write the reaction, right? So
okay.
that is my delta H, right? So that delta H basically my bond enthalpy. But you know how to connect your bond enthalpy with the bond dissociation enthalpies, isn't it?
Yes, sir.
Right, that you
Yes.
can do. And that obviously that delta H again can be equated to what? Again can be written in terms of enthalpies of formation, enthalpy of formation of products minus enthalpy of formation of reactants. And that's it. You will be finding the answer.
Okay, sir.
Right? Okay,
Yes, sir.
cool. So now let me ask, maybe, whom should I ask? Mithun, are you there, Kana?
Sir,
Can you tell me, I have, if I write bond enthalpy, how will you write the bond enthalpy reaction for SF6?
1 minute, sir. I'll say I am doing, sir. 1 minute, sir.
Yeah. So hope you understood my question. It's pretty simple. You don't have to even go through the question, Mithun. Just answer my question. I'm asking, how will you write the reaction for bond enthalpy of SF6?
Sir, the bond enthalpy for SF6, sir.
Yeah. If I say bond enthalpy of SF6 is some value, how will you
No,
give
sir.
the equation?
Should I say the energy amount, sir, that kJ per
No.
kilojoules per mole, sir?
Just tell me the reaction.
Yes, sir. Sir, it's the delta SF.
No, I think you're not getting the question. Just tell me the reaction. How will you write the reaction for bond enthalpy of SF6? What we have to do in bond enthalpy, or it is also called as enthalpy of atomization, isn't it? And you know the definition for this. I have to convert molecule into atoms. That's what I need to do. Correct. So the molecule here is SF6. So what are all the elements present here? You tell me, Mithun. I'll help you get the answer, but you're going to tell me what are the elements present in SF6.
Fluorine, sulfur.
Correct. Fluorine and sulfur, right? So I have to convert SF6 molecule into its element in atomic state, right? So now can you give me the equation?
Sir,
Yeah.
sir, I joined late because I have a problem with my internet, sir.
Okay, but
I'm changing it.
anyways, but that is not a good enough reason. We have been doing this for the past almost 1 week. You are supposed to answer, but still, I'm letting you go. But next time, Mithun, you
Sir,
are
no,
answering.
sir. You didn't. I'm not the person who asked the question.
Oh, okay.
I
I'm
joined
sorry.
just now.
Oh, who is that? Is that
I'm Surya, sir.
Surya. Okay, Surya. No issues. No issues. Fine. Yes, Mithun. I think now Mithun can answer. I'm sorry. It was a bad judgment. Anyways, so tell me, people. Tell me, Mithun. So how will I write the reaction? Mithun, hope you're there. Okay. I think there is some problem. I don't know. But Mithun, I really expect you to answer these kind of questions. Right. Anyways, Pranav, are you there, Kana? Maybe in the chat, you'll be there. Okay. Pranav, are you there? Pranav, can you tell me the reaction? Bond enthalpy of SF6. SF6 gives S plus F, just F. Anything else before F? That's 90% correct what you wrote. There's just one thing missing.
Del F.
Sorry? How many atoms of sulfur are there? See, how many atoms of fluorine are there? You have SF6, you have one sulfur atom, so you wrote S. But F, how many atoms
S
are there?
plus 6 of, sorry,
Ah,
S plus 6
correct.
of, sir.
Right, so it should be correct. Thanks, Pranav. That's a good attempt. Right, so how will I write the reaction? I'll write it as SF6 gives S plus 6F. This is how I write the reaction, as simple as that, bond enthalpy. Right, so obviously here the bond enthalpy, one second people, there are some dust here, that's why it's little, okay. Okay, so what happened here? Okay, right. So bond enthalpy, I'll write it as okay, fine. So again, I'll ask someone. See, I know that I'm wasting a little time, but I really have to make sure that everybody understands. Like, that's why I'm asking so many questions. Please bear with me. People who already got the answer. Okay. So yeah. So let me ask the Bavadarani.
Yes, sir.
Can you tell me how will you write? This is the bond enthalpy, obviously. Now, how will you write it in terms of bond dissociation enthalpies? I'm not
Sir,
asking.
I wrote bond dissociation enthalpy of sulfur and fluorine is 6 BDE
6 BDE of
S sulfur and
fluorine bond.
fluorine.
Yes, absolutely right. Right. So the overall bond enthalpy will be equal to 6 into bond dissociation enthalpy of SF bond. So you can understand there are 6 SF bonds in this molecule, and all those has to be broken so that this is going to come out as product. So the overall bond enthalpy will be equal to 6 into the bond dissociation enthalpy of SF bond. Right. Now this is the overall enthalpy here. Now this overall enthalpy again can be written in terms of enthalpies of formation. Correct. So I can write 6 into bond dissociation energy of SF bond will be equal to, now if I write it in terms of enthalpies of formations, it will be enthalpy of formation of products minus enthalpy of formation of reactants, right? So how can I write it? I can write it as delta HF of S sulfur atom plus 6 into enthalpy of formation of fluorine atom, because I have 6F here, and coming back to the reactants minus enthalpy, oh god.
Sir,
Yeah,
sir, I did this step before finding the bond dissociation enthalpy itself, sir. Is it
doesn't
right?
matter, doesn't matter how, however you want the steps, the sequence of stuff doesn't matter, but you just have to get the answer properly. But again, all those things has to be mentioned. Where you mention it doesn't matter, it's okay.
Okay, sir.
Right. Right, so I have minus delta HF of, oh god, there's some problem here again. Maybe let me try to write it down, maybe it will come. Okay, okay, minus delta HF of SF6. That's it. Right, so you have to plug in the values. So this is what you need to find, isn't it? Bond dissociation energy of SF is what is asked, right? So you know this value, this value, this value, do whatever it is and multiply, divide it by 6. That is what is going to be your answer. Okay, so if you want the final answer, I can give you the final answer. 1 second.
Sir, is it
So
minus 125?
hey, 1 second. 13 is no, it's plus 309.16. The answer is 309.16 kilojoules. This would have been the answer. I think there is some calculation mistake which you have done. Please check it.
Yes,
Right?
sir.
Okay, cool. So yeah,
Yes, sir.
people. So that's about the problems. Okay. Right. So and obviously this is not going to be enough if at all you want to master it. Right. So but I think this should be enough for your board exams. I mean, sorry, your school exams. Right. This is going to be, we did very good quality problems. You will not see this kind of problem in your NCERT textbooks. Not that, like, I don't think they will ask you this kind of questions in your exams also, but you are already over prepared. Right. So be proud about it. Okay. So we'll go on. We'll go on to the third part of the chapter. Okay. Right. Fine. So hope everyone is ready. Now you're not going to do problems. We are going to see something in some interesting things in thermodynamics. Right. Okay. Now second part of the chapter is actually going to talk about, sorry. Yeah. Second part of the chapter is actually going to talk about this particular stuff which I'm writing. It's called entropy. Okay. Fine. Has anyone heard this term before? Entropy? In your lower classes, or someone telling, have you ever
No,
heard this term? Okay, so fine. So I don't expect you to, this is obviously not for lower classes people, even though you have studied about heat and other stuffs, right? But studying about entropy, yeah, this is the, like in learning 11th, you'll be hearing this term. Okay, fine. So when I say entropy, okay, so entropy is what? Entropy is basically a measure of disorderliness. Right, as simple as that. This is the catch I have, right? So my entropy is basically a measure of disorderliness, or I would say it's a measure of chaos. How disoriented, how random sorry right? So how random the system is, right? That's what is called as entropy of a system, right? Okay, now if at all you want to understand a little bit, if you give you an example, maybe you'll understand. Okay, say for example, I have solids, I have a solid, I have a liquid, I have a gas. Okay, right? Fine. So we know in solids, obviously all the particles are perfectly arranged, right? They have a proper shape, they have a definite volume and all that, right? Again, liquid, if I go again compared to solids, they're not that properly arranged, but again they are little properly arranged. They have a definite volume is there, right? And shape, yes, they can take the shape of the container, as we already know, right? Now when I go to gases, gases are really not going to be direct, or to say properly arranged. It is proper random arrangement of atoms there and there right? And obviously they don't have proper shape, and they are going to take up whatever volume you're going to give them. That's what we studied in gaseous state, isn't it? So if you ask me, or if I ask you that among solids, liquids and gases, right, which is going to have maximum entropy, what will be your answer?
Yes.
Gases, right? So as I told you, entropy is basically the measure of disorderliness, right? So more and more is the chaos, more and more is the disorientations, right? More and more is going to be the entropy. Now, just now as we discussed, right? So gases will have more entropy than your liquids, and liquids will have more entropy than the solids. This is a very simple way to understand. Okay, right? Now what other things I can tell you? Okay, maybe something like this. Okay, see, I have a gas at okay, say I have a gas at say some 25 degree Celsius, there is a gas, and say the same gas is there at 100 degrees Celsius. Okay, now say this is case 1, this is case 2. Now, where do you think the entropy is going to be higher? Same gas is there at 25 degrees Celsius. The same gas is there at 100 degrees Celsius.
100
Where do you-
degree.
100, sir.
Easy, right? Obviously, if I have 100 degrees Celsius, the molecules will have more energy. They'll be randomly moving with so much velocity, right? Obviously, the disorderliness, the chaos is going to be more in this case. So obviously, the gas which is having it is at 100 degrees Celsius will definitely have more entropy, right? So again, so hope you understand the whole picture. What do you mean by entropy? Okay, now see these are some small implications of whatever you're doing, but when we see the actual aspects of how much your what to say, how much your entropy is significant with respect to chemical reactions, or say with respect to very big phenomena, you are really going to appreciate what we are going to learn. Okay, fine. Now so now that we have understood what is entropy, right, now there is a law. Like I told you, that we already saw 2 laws of thermodynamics, that is the 0th law of thermodynamics and your first law of thermodynamics, right? So your second law of thermodynamics is basically going to deal with this entropy. Okay, but before we are going to see what exactly the law says, right, you have to understand how am I going to represent it. So please understand entropy is represented by the letter S. Okay, so capital S. Okay, now again, how do you measure this S? How do you measure the absolute entropy? The answer is you cannot measure the absolute entropy. Just like you cannot measure the absolute enthalpy values, you cannot measure the absolute internal energy values. Just like that, you cannot measure the absolute entropy values. But what you can measure, right? What you can measure is delta S. That is, when you change, when there is a change in entropy, let's say for example, in a solid becomes a gas, or say I increase the temperature of the gas or decrease the temperature of the gas, something like that, right? Or say in the reactant, for example, there is a reaction in which say I have a solid in the reactant side, right? And say I'll give you an example. For example, I have say CaCO3. When I heat it, becomes CaO plus CO2. There is really a problem at this particular point. I don't know why this is happening. Anyways, so hope you understood. Anyways, I can write it again. Okay, so CaO plus CO2, right? Now you can obviously see that this is a solid, and this is a gas. Okay, there's a problem with the touch screen somewhere. Anyways, right, so hope you understood the equation. So I have CaCO3 solid becoming CaO solid and CO2 gas. Now what do you understand from this? If I ask you whether the entropy is decreasing or increasing, what will be your answer for this reaction? Increasing, right? Because in the reactant side I had only solid, but in the product side I have a gaseous molecule. So obviously now just now we saw gaseous molecules are going to have more entropy, right? So whenever you see reactions like this, right, I have a solid or a liquid getting converted to gases, so definitely for those the entropy is increasing, right? Or in other words, if I have lesser number of gases in the reactant side and more amount of gases in the product side, again I would say that the entropy is going to increase there. Okay, so anyways, so that's what I told you. So you can see that there is a change in entropy. Initially I would have had some entropy here and the entropy would have been changed. So the difference in entropy, that we'll be able to find out, and that is what is my change in entropy, that is my delta S. This is what we'll be able to measure for all the things. This is for a physical process or for a chemical reaction. So this delta S is the only thing which will be able to measure. Is that okay? Right, now there is a definition. Right, now, okay, definition which you have already seen. I'm going to give you a mathematical definition. Okay, so the mathematical definition of delta S goes like this. It's equal to Q reversible divided by,
So Q is heat, sir.
yeah, Q is the heat, right? So delta S is equal to Q reversible, REV represents reversible, divided by T. T is temperature and absolute Kelvin, temperature in Kelvin. Okay, so this is the mathematical representation or mathematical definition of delta S. Don't ask me, sir, how is it like this, right? But don't ask me, sir, how is it derived? It is not a derived quantity, right? But you can actually understand why this equation is like this through the logic. Okay, so please understand. Okay, so they are telling the change in entropy. The change in entropy here is directly proportional to the heat. Yes, understood. Just now we saw in the 25 degrees Celsius case and the 100 degree. Okay, or let me put it in this way, right? Right. So from here to here, right? I'm going from state 1 to state 2. I gave say 100 joules of heat. Right, I have the same gas initially. For this gas, I started heating it and I supplied 100 joules of heat. So definitely the entropy in this case would have got an increase. The final entropy is higher than the initial entropy, right? So now I'll tell you why is it Q reversible. We'll come back to that later. But for now, what you have to understand is if I supply heat, right? If I supply heat to the system, definitely the molecules are going to gain more energy, so they're going to move still more randomly. So obviously this delta S and your Q are directly related. Okay, right. Now next thing is you have to understand why that temperature is in the denominator, in the sense that why is it that delta S and temperature are inversely related. Okay, right. Now you say if you look at the last question, like I told, it's 25 and 100 degrees Celsius. Now you said that obviously at 100 degrees Celsius, I'm going to have more entropy. Yes, absolutely true. But we are not talking about change in entropy here, people. Please understand that, right? So we are talking about the absolute entropies in this case. Obviously, the absolute entropy when I have 100 degrees Celsius is greater than when I have 25 degrees Celsius. But we are talking about what? We are talking about change in entropy. We're talking about change in entropy. Obviously, the absolute entropy will be directly proportional to the temperature, no doubt. But if I want to talk about change in entropy, obviously, okay, you can understand if I give you a case, maybe. Okay, say again. Okay, fine. I have a gas at say 30 degrees Celsius and I have a gas at 50 degrees Celsius. Okay, so to both of them, I give some 10 joules of heat. Okay, so one gas is at 30 degrees Celsius, the other gas is at 50 degrees Celsius. To both of them, I give 10 joules of heat. Okay, now think and tell me, obviously in which case the entropy would have been higher. I mean, increase in entropy. Obviously in both the case, entropy is going to increase, no doubt, right? But what I'm asking is, if this is case 1, this is case 2, right? In which case the change in entropy is higher?
The first one is 30 and second one is 50, sir.
Yeah, first one is 30 degrees Celsius initially. This is at 50 degrees Celsius. And for both of them, I'm giving 10 joules of heat.
50 degrees Celsius, sir.
Sorry?
50 degrees Celsius.
Okay, that's what we think. But please understand, okay, see, if I'm going to, it's already at a very low temperature. That means its initial, its initial entropy is less. Obviously, here the initial entropy is little higher. Right, now in both the cases I'm going to have increase in entropy, no doubt about it. Correct, right? Now here say I'll give you a rough estimate, right? Say initially okay, let me mark a new page, right? So let me draw the diagrams again. Say this is at what did I say, 30 degrees Celsius, right? And the same gas is at 50 degrees Celsius. Okay, and to both of them I give 10 joules of heat. Okay, so as I told you, right, if I look at initially the absolute entropy, in which case is going to be higher, definitely in 50 degrees Celsius, the absolute entropy, the initial entropy itself is higher. Okay. Now in 30 degrees Celsius, the entropy is lesser, no doubt, right? Now I'm giving 10 joules of heat to both of them. Okay, I'm giving 10 joules of heat to both of them. So in both the cases, there is going to be increase in entropy. Definitely, there is no doubt. Now the question is where where I'm going to have a higher increase in entropy, right? Now please understand, here the entropy is already higher, right? In 50 degrees Celsius case, the initial entropy was already higher, so making it still higher is going to be little difficult. But here, if you check, the initial entropy was less, so for the 10 joules, see, you're giving the same amount of energy, is it not? For the same amount of energy, obviously here the increase in entropy would have been higher because the initial entropy was less. Here the increase in entropy is going to be little less because the initial entropy was already high. Hope you understand what I'm trying to say. Yes, did you get my point?
Yes, understood.
Okay, again I repeat. See, initial when I have 30 degrees and 50 degrees, initially definitely the initial entropy of 50 degrees would have been greater. No doubt, absolute entropy, right? Now for both of them, I'm giving 10 joules of heat, right? So obviously in both the cases, the entropy is going to increase, no doubt, right? Now, initially the entropy of 30 degrees was pretty less, right? So I would say it is very easy for it to undergo an increase in entropy by absorbing this 10 joules, right? But it is going to be little difficult for the 50 degrees Celsius to increase in entropy because the entropy is already higher. Hope you understand. Or if I give you in terms of values, okay, say initially, let me say that the initial entropy was 5 and say the initial entropy was 10, assuming. Okay, right, the initial entropy was 5 and 10 for 30 degrees Celsius and 50 degrees Celsius. Okay, now I'm giving 10 joules of heat. So please understand, for the, if I'm going to give you the same amount of energy, right, if I'm going to give you the same amount of energy, I would say that, say, same amount of increase is only going to happen. Say, for example, for 10 joules of heat, I can say that the entropy might increase by 5. Okay, the entropy might increase by 5. So initially it was 5. Okay, now, oh wait, no, that is not a good explanation. Okay, so if I say it's 5 and 5, again the delta x is 5. No, like, oh, okay, this is not a good analogy. Please bear with it, right? But hope you understand what I'm trying to say, right? Here, initially the entropy is lesser, so increase in entropy is higher. Here, the increase in entropy is lesser because already the entropy is already higher. I mean, initially itself the entropy is higher. Okay, so that is the reason why you have this particular equation. Delta S is equal to Q reversible, to be very exact. So Q reversible divided by T. Okay, fine. So we understood what is the logic behind this equation, right? Why is there Q is in the reactance? Sorry, Q is in the numerator because obviously the more and more heat I supply, more and more will be the increase in entropy. And obviously temperature, if we're talking about the initial temperature of the gas or initial temperature of the system, right? So obviously higher the temperature, difficult it is for me to increase the entropy, right? So in that lesser temperature, with even a small amount of heat given, the entropy increase is going to be very, very high. That's what I'm trying to say, right? So this we understood. Now, can you tell me from this, what will be the unit of delta S, or say the entropy? What will be the unit? Just look at the equation and tell me what will be the unit.
Joules per Kelvin, sir.
Yes, right. So for Q, I know it's joules. For temperature, I know it is Kelvin. So obviously the unit of delta S is joule per Kelvin. Okay, joule per Kelvin is what is the unit of S, or delta S for that matter. Okay, fine, people. I think we'll stop with this for today. Okay, I just introduced to you what is entropy and what is the mathematical definition of entropy, and we just saw the units. Okay, so I think this should be sufficient. So next class I think I'll be completing this chapter. There are no problems as such. It will be like for JE level, yes, you will be getting problems from this also. But for your school level, you don't need to know you don't have to know how to do the problems as such. But if you're interested, yes, we can have a class for that. We can do problems on this also. No issues at all. Right. So yeah, thank you, people. Is there any doubts if you want to ask?
No, sir.
No, sir.
Okay, cool then. So you can go take some rest and go attend your school classes. I'll just stop sharing.
Thank you, sir.
Thank you,
Yeah,
sir.
thank you. You can go. Thank you so much.